Okay, so I now want to talk about symmetric boundary conditions. So we have our operator up here. It's the second differentiation operator. And we're going to change our domain. We're going to say the domain is going to be all U's that satisfy a symmetric boundary condition. Symmetric boundary conditions. Now, I haven't told you what a symmetric boundary condition is. It's a generalization of the boundary conditions that we've looked at. So Dirichlet boundary conditions, Neumann boundary conditions, these are all examples. Periodic boundary conditions, Robin boundary conditions, these are all examples of symmetric boundary conditions. And so when I say U satisfies a symmetric boundary condition, I mean there's a fixed boundary condition, as a fixed symmetric boundary condition that U satisfies. So it's a general class of boundary conditions, but to make this problem well defined, we have to assume that U satisfies a fixed symmetric boundary condition. Okay, so what's a symmetric boundary condition? I haven't told you what a symmetric boundary condition is. So a symmetric boundary condition, is a condition a boundary condition, sorry, such that if phi and psi satisfy it, then the following is true. If I look at phi times psi prime, and I evaluate, do the A to B, psi of B, or phi of B, psi prime of B, minus phi of A, psi prime of A, that this minus, let me just make sure I have this correct, minus phi prime psi AB, this is equal to 0. Okay, so symmetric comes from the fact that it's phi psi prime here and phi prime psi here. I mean, the other way we could write this, if we cover up the 0, we could make that equal to, make that equals there. And so this is where the term symmetric comes from. Okay, well, how can we, so what the theorem now is going to say is that if LF is equal to lambda F, and LG is equal to gamma G, and F and G both satisfy the same boundary condition, then F and G are orthogonal with respect to this inner product here. Okay, so why is that true? Well, let's see how things are going to change over here. So I have the integral, so this is what I want to show. I want to show this integral is 0. Now, again, I'm going to use the fact that if minus F double prime is equal to lambda F, then F is equal to minus F double prime over lambda, so that's where this comes from. Okay, going from here to here, it's the same that we did yesterday, only now the difference is going to be that this is not necessarily equal to 0. So this thing right here is not necessarily equal to 0. Okay, so what we're going to have, I'm going to erase this line right here because I can't do any further simplification. I can't assume that this is equal to 0. Okay, so now instead of having what I had before, I'm just going to sort of copy and paste things down here. So this is minus 2 over lambda L. We're going to have F prime G 0 to L minus the integral from 0 to L F prime G prime. Okay, so now what's this going to be equal to? Well, this is also messed up now because I have this boundary term. Okay, so now what I'm going to do is I'm going to do integration by parts here again and move the F prime to the G prime. And so I'm going to have my minus 2 over lambda L on the outside. This is still going to be there. So this is F prime G going from 0 to L minus, okay, so now I'm going to forget about, I wrote the minus sign. That minus sign is that minus sign. So forget about that minus sign and just work with the integral. So I'm going to be doing integration by parts. So I'm going to have, I'm going to be doing integration by parts, and I want to take the derivative off of F and put it on G. So this is like my V prime, and this is like my U. So it's going to be FG prime from 0 to L. Okay, and there's parentheses here, so it's minus the integral, but there's a minus sign, so it's going to be plus. So Now it's plus the integral from 0 to L f g double prime. Okay, but now f and g satisfy the symmetric boundary conditions, and by definition, it means that's equal to 0. Okay, so it's the same thing, except over here I'm using Greek letters, and over here I'm using f and g. Okay, so by the symmetric boundary conditions then, it's not that each boundary term individually is 0, but this is equal to 0 by the symmetric boundary conditions. Okay, so that's equal to 0, and now this line is equal to this line, and all of the other reasoning follows. Okay, so there's just this point in the middle of the proof where we have to do, use these more generic boundary conditions. Okay, so this tells us that if we have symmetric boundary conditions, then the eigenfunctions are still going to be orthogonal with respect to this inner product. Okay, and then a generalized Fourier series is going to be a Fourier series, and the eigenfunctions are now going to be the eigenfunctions are now going to be satisfying the symmetric boundary conditions rather than the easier boundary conditions that we've been looking at so far. But the good news is, so the bad news is they're going to have complicated formulas. The bad news is the eigenvalues are going to have complicated formulas. But the good news is the functions themselves are still orthogonal. So from a theoretical perspective, we can still do all of the orthogonality stuff that we wanted to do. Remember, a few videos ago we showed why orthogonality was important, and these are also going to be orthogonal. Now, one thing that's going to turn out to be different is that the 2 over L is not going to be like we're doing it with respect to the weight 2 over L. It's not necessarily going to be 2 over L. It's going to be a different constant with respect to which these functions are going to be orthogonal. I mean, it could be 2 over L, but then anyways. My point is that the inner product here might not be the exact right one. Instead of 2 over L, it might be a different constant. But that doesn't change the fact that they're still going to be orthogonal. Okay, so that's it for this video. In the next video, I'm going to actually look at an example where we have a symmetric boundary condition that's a little more complicated than what we've looked at. And this would be helpful for the homework.